Okay. So stepping back in time a little bit to catch up on a lecture that I haven't gotten to before the exam. Finishing up the last bit of spectroscopy, which is infrared spectroscopy. So infrared is the region of the wavelength just higher than the red visible light. And we have two regions that are most relevant for us in the analysis is the near infrared, which is just by the red visible light, and then the mid-infrared somewhere in the middle region of the infrared. So, and these are the wavelengths. Just as a reminder, larger wavelength is associated with smaller energy. So the infrared has larger wavelengths than the visible light, so they carry less energy. And these terms we will encounter today about the dispersive versus Fourier transform. These are two types of instrumentation for the use of IR. We'll talk about the difference between dispersive units and Fourier transform units. And in IR, we either rely on measuring reflectance, or the light reflected, or we measure the transmitted light. And we'll talk about that. We can use IR spectroscopy for qualitative measures or quantitative measures. And some applications, from your knowledge, where do you think we apply IR spectroscopy? From what you know in the past encounters. Huh? Identification. Yes, identification of adulterant, for example. FTIR has been used to identify the presence of melamine in infant formula, for example. Okay, what else?
Quality assurance.
Quality assurance, measuring certain components to determine a consistency of quality. Yep.
Quantification.
Quantification. Oftentimes food composition is measured online during processing using IR instrumentation. Mid-IR is commonly used for milk, for example. Near-IR is used for a lot of different processes or products. Okay, so we talked about identification, qualitative detection, whether it's present or not present, quantification, compositional analysis, quality assurance, and forensics, and structural elucidation. That means determining the functional groups present within a certain compound. Okay, so many applications for IR. So IR analysis is non-invasive. That means you can analyze your sample. It's not a destructive method, and you can reuse the sample for other analyses. It's very rapid, a quick analysis. You rarely need any sample preparation. In most cases, you want to make sure that you have consistent particle size. So you grind your samples and make sure if they're solid, that is, they are of consistent particle size. That's very important for measurements. It's suitable for routine and quick analyses, and it is energy efficient and environmentally friendly. So basically, it's similar to any spectroscopy. So you have a radiation source, and in this case, it's an IR source. And then the IR radiation hits the sample. And if it is really liquid sample, often it is measuring transmission. So some light is absorbed, other is scattered or reflected, and then the remaining light is what is measured in this case. In IR spectroscopy, we're measuring transmittance, not absorption. And the transmitted light gets to the detector and generates a spectra, and this spectra is unique to your sample, is unique to the components, it has a fingerprint characteristic. No two structures have the same fingerprint, so it's highly specific. So it's based on, IR spectroscopy is based on measuring changes in vibrational energy. And the vibrational energy in the spectrum of energy are these grades within the electron or electronic state. So you don't have enough energy to shift electronic state, so your electrons don't shift to higher shell. What happens is vibration of the bonds occur. So the molecules are in constant motions, and then the atoms are bound. So the bonding or the bonds are in constant motion, and these bonds change in vibration based on the IR absorption. If they absorb IR radiation within the allowable potential change in their energy or in their vibrational energy, then they can absorb that particular IR radiation. So again, the energy is quantized, as I explained earlier in spectroscopy, introduction to spectroscopy. So only allowable energy changes, if the IR light carries the allowable energy changes, then the molecule will absorb that light. And it can be measured in terms of its frequency, so energy equals the constant multiplied by the frequency. So in IR, you often hear or you plot wave number across or against transmission instead of wavelength. In absorption, you have wavelength on the x-axis and absorption on the y-axis. In IR, you have transmission on percent transmissions on the y-axis, and on the x-axis is wave number. And the relationship between wave number and wavelength is basically wave number is 1 over wavelength in centimeter. So then when you see a plot of spectroscopy, you'll see that the unit is per centimeters, or centimeter to the negative 1. So your bonds are, the covalent bond is kind of a spring-like, and it has either stretching movement or bending movement. So stretching is the bond stretches symmetrically or asymmetrically, and the bending that you change in the angle of the bond. So stretching and bending is both can be vibration. So like I said, if the frequency of the radiation matches the allowable vibrational frequency of the molecule, then the radiation will be absorbed, causing a change in the amplitude of the molecular vibration. So there's always constant vibration, but once the molecule absorbs light, there is a change in the energy of the vibration, or the amplitude of the vibration. So here's a very common spectra, mid-IR spectra, and in this case it's a butyryl aldehyde. So what you can see here is different bonds absorb light at different wave number. So here you have carbonyl, so you would have this kind of stretch, absorption at 2,750, and then you have a CH stretch, and then here a C double bond O stretch. So it's very unique, so you can kind of elucidate the structure of butyl aldehyde. So identification or structural elucidation. So different groups, functional groups within a molecule have different absorbing features or bonds and different frequency or a different wave number. So this is just to illustrate that we can identify these different groups by monitoring their absorption or the transmission of light at particular wave numbers. So can we employ IR radiation for mineral analysis following atomic absorption technique? Why not, Nick?
Because you atomize them, so there's no bonds.
So no bonds, they're atoms. We don't have vibrational energy. So type of instrumentation, so there's a dispersive instrument. In this case, it's very similar to regular UV vis spectroscopy, where you have a monochromator, so the light is dispersed into individual radiation or wave numbers and then sequentially passed through the system, one after the other through the sample, and then a spectra is generated. And then we have a double beam, that means you have the light is split into two, one goes to a reference cell and one goes to your sample, so that you always subtract the transmittance is already taking into account your blank or reference cell. So the radiation source and detectors, that's just FYI, you don't need to memorize that. Okay, so dispersive instruments are phasing out, so there's not much out there, not many out there in terms of mid-IR instruments. What is common is the Fourier Transform. Is most common and mostly used is the Fourier Transform system. And here the radiation is not dispersed. That means you don't have diffraction of light into multiple wavelengths. What you have is that the light gets projected to your sample simultaneously, and a spectra is generated simultaneously at multiple wavelengths. So instead of a monochromator, you have an interferometer. So I don't know if you remember, but we talked earlier, first lecture on spectroscopy, about constructive and destructive combination of wavelengths, where two wavelengths meet in space, either in a constructive manner or in a destructive manner. In a constructive manner, you have amplification, where the highest point is increased and the lowest point in an oscillation is increased. So you get higher intensity or higher energy of that particular combined wavelength. So this enhances sensitivity. And destructive, sometimes you want to eliminate the wavelengths that you can get noise, instrumental noise at, or interference. So you can eliminate the wavelength that might cause interference and increase the noise of the instrument, whereas you can multiply a specific wavelength that you want to enhance the sensitivity of detection at that wavelength. And this happens by projecting the light at multiple mirrors at different angles, where the light gets, or the wavelengths meet in space for either amplification or cancellation. So in IR you have different modes, either transmission IR, attenuated total reflectance, or internal reflectance cells. So these are three types. What happens with transmission is basically you're measuring liquids. So light can actually go through, get whatever is absorbed, and then the transmitted light can be measured. It can be used for solid as well if it's dispersed, for example, in mineral oil or pelleted with potassium bromide. Then again, you can measure transmittance in this case. Cell windows should be non-absorbing material, such as halide, sulfide salts, zinc selenide. Cannot use glass or quartz because they absorb in the mid-IR region. Attenuated total reflectance, this is used for solids, paste, and viscous liquids where light cannot be really transmitted through. What happens here is when the light hits the surface, it gets reflected, and part of it gets absorbed. So you're measuring the reflected, and the reflected light is less than the actual emitted light because some of the light got absorbed by the components. Internal reflectance, it can be used with liquid sample where light penetrates slightly and then gets reflected. So it penetrates just a few micrometers into the liquid and then it's reflected back. And then you're measuring the reflected light, which is less than the original light, given that some light got absorbed by your components in your liquid sample. We can have multiple interfaces with the IR. For example, gas chromatography can be linked to IR, where your components coming off of the column after separation can be identified and structurally elucidated by FTIR. Or you can link the FTIR to a microscope where the light is focused through the microscope onto a thin specimen mounted on a microscope slide, and then you can get a spectra of that component on the microscope. It's a pretty neat technique. It's actually often used, for example, to measure migration and crystallization. So migration of water or crystallization. So you can actually have a kind of a kinetic. So you can look at you can project the light at a certain location on the slide and then move the light a little bit and then look at changes across a certain specimen. It's pretty neat to look at migration and differences within one sample. It's mostly used for quantification. Most common one is the IR milk analyzer, where you can follow Beer's law to quantitate. And basically for fat, you're measuring the carbonyl. For protein, you're measuring amide vibration. And for lactose, you're measuring hydroxyl groups vibration. However, in order to get accurate quantification, you have to calibrate the instrument. So usually what they do, you have standard milk samples that vary in protein, fat, and lactose, so that you cover the whole spectrum of concentration of different milk samples. And these standards are run through the instrument and as well as analyzed by official methods of analysis. So fat would be analyzed, let's say, by Mujiner, protein by Keldal, and lactose by a lactose assay. And then you go through and calibrate the equipment with the actual values you've gotten from the actual methods of analysis. We call those primary methods of analysis, and then IR is a secondary method of analysis that is based on or calibrated using the primary methods of analysis. So mid-IR instruments using FTIR to measure absorption at many wavelengths simultaneously and apply multivariate regression analysis to predict the concentration of each constituent. This is recap question to ask at the end, but moving on. Raman spectroscopy is another form of IR spectroscopy. It's based on scattering of light and measuring the difference of scattered light that is less energy than the incident light. So there is scattering is the scattered photon that has the same energy as the incident light. So when light hits your sample, and then the sample vibrates and then releases energy, it's the same energy, in this case, as the incident beam. So the scattered photon has the same energy as the incident beam. In Raman scattering, some of the components actually absorb the light, and then they don't return to the same vibration level, they go to a higher level. So they go to a higher vibration level, and that's what gets detected. So the difference in frequency between the incident and scattered light is equal to the frequency of the vibration of the molecule. So in this case, the scattered photon has less energy than the incident beam because the particle did not go back to the original vibration state and went back to a little higher energy state. So the source of radiation is mostly a laser, and you can use Raman to quantitate. So intensity of light scattered at a specific frequency is directly proportional to the concentration of scattering molecules present. So the molecules that were able to scatter the light. It can be applicable to both solids and liquid, and this is advantageous because for Raman spectroscopy, the water is not absorbent or does not have a Raman response, whereas water has high absorption in the IR region. So that's liquid sample can be measured. So you can measure concentrations of different compounds in aqueous solution, which is advantageous compared to IR, where the water absorbs quite a bit in the IR region. Spectrum is less complex, which is advantageous, so you can actually integrate and analyze the data easier with Raman versus IR spectrum. Near IR is more widely used to quantitate composition. You can measure directly the composition of solid food, and mostly it's based on diffuse reflectance technique. So what that means here, in this case, your light hits your surface of a food product. Let's say if it's a solid food product, evenly sized particles, so they're ground to even particle size, and then the light hits them. Some of the light gets reflected. Some of the light actually get absorbed. So they diffuse in a little bit, and some of the components absorb the light, and remainder of the lights get reflected. So the remainder of the light that gets reflected is what gets analyzed by the detector. So when the radiation interacts with the sample particle, the chemical constituents in the sample can absorb part of the radiation. That's what happens when the light goes in. Some of your particulates or components, constituents absorb light, and the remainder of the light gets reflected back, and that's what gets measured. It's very important to control particle size and shape, so it's very important to have a homogeneous sample, since that will impact how the light gets diffused and how it reflects back. So absorption bands in the near IR region are primarily overtones and combination. That means your peaks are broad. Overtones, they can overlap each other, and they are weak in intensity. And the absorption is primarily from functional groups that have an hydrogen atom linked to carbon, nitrogen, or oxygen, which are common groups in water, proteins, lipid, and carbohydrate, which is perfect for determining the composition of different foods. So in water, we're measuring OH stretch at two different regions. For proteins, you're measuring amine deformation at also two different regions. Lipid, you measure the methylene stretch in that particular region, and also methyl groups at this two different regions basically. Carbohydrate, you measure the CO and the OH stretching combination at this region. So you can really determine water, protein, lipids, carbohydrate, but there is an overlap between them. So this is, for example, a cheese sample, and this is what we mean by broad and combination. So you don't see really sharp peaks. It's broad peaks, and you really need to deconvolute the peaks and do multiple regression analysis for quantification. And this can be done by computer systems. You don't usually do it yourself. So, for example, cheese is high in water, so you can see this peak over here and this peak over there. They're really big and broad and overlapping protein, for example, and lipid portion. So the water is overlapping the protein and lipid in the cheese, whereas in wheat, you can see there's a less water, so you see this peak here and peak here are much smaller, so you have less water, and then you have protein and lipid separated. In egg white, you can see the protein here and combined with the lipid, because in egg white you can have higher protein concentration than in wheat, so you see that peak broader. But anyway, calculations, mathematical calculations will allow for accurate quantification. Radiation source in an IR is tungsten halogen lamp with quartz envelope. Quartz does not absorb in this near IR region, so you can use quartz cell. You can either have a monochromator or interferometer. As I said, interferometer is most common now with IR instrumentation. Allows for rapid scanning. The entire radiation is dispersed, and you get spectra in less than a second. Using Fourier Transform technology to determine or to convert the energy into spectral data. Detectors, for FYI, you don't really need to know. So measurement in IR, either you measure reflection or you measure transmission. Reflection is mostly for solid food that are tightly packed into the cell against your quartz window, and then you measure the intensity of light that gets reflected from the sample compared to non-absorbing reference. So part of the light gets absorbed by the different components, and the remainder of the light gets reflected, and that's what you measure, and then the computer generates the absorption or the transmission spectra or reflectance spectra. You can be measuring transmission, and in this case is the light goes through the sample, whatever gets absorbed, and the remainder of the light gets transmitted, and you measure that, and that's mostly for liquid samples. So reflection or transmission is what you measure in this case. You can do qualitative analysis, and you can do quantitative. Quantitative analysis is done by the computer where you do multiple regression, linear regression analysis, because your peaks are overlap. They're not sharp peaks, so multiple linear regression is often used to quantitate different components. So calibration is done using either partial least square regression or principal components. So mathematical operations that the computer actually does for you, or the software does for you. And after calibration, you often validate with an independent set of samples. So once you've calibrated, then you run a couple of samples of known concentrations so that you want to make sure that the calibration was done accurately. So it's widely used to determine composition of grains, cereal products, oil seeds, or oilseed products. They're common. Some of the methods for cereal is actually AACCI approved methods. So they are official methods. Once calibrated, they are considered official methods of analysis. Used a lot with dairy products, butter, cheese, milk, whey powder. But remember, calibration is key for quantitative analysis. It can be used for identification of contaminants, and here's an example where this is the IR spectra of infant formula, and this is the IR spectra of melamine. If melamine is present in your infant formula, then you will see certain stretches and bending of the bonds at particular wave numbers, and you can detect whether melamine is in your sample or not. So can we use near IR for online measuring of constituents during processing? Can you? Wake up. Can we use IR, near IR? What do you say, Anne?
Yes.
Yes.
Why couldn't you?
Why couldn't we? Yeah.
Right.
Right. It's not a trick question. Yes, you can. It's a quick, fast method. If it's calibrated, you can determine moisture content really fast. You can determine ash content really fast. Let's say you are producing flour and you need a certain degree of refinement. So you want to test if your mill is working properly. So you go take a sample of flour and go measure the ash content. If it's high at a certain level, that means you probably did not achieve 80% refinement. You achieve 50% refinement. You go back and adjust the mill to reduce the bran. So that's an example. So there is a list of advantages and disadvantages for mid-IR and near-IR. Just review them on your own. With that, that's the end of this lecture. Zach, do we start a new lecture?
No, we go to recap questions.
What are some applications of IR spectroscopy?
Structural analysis.
Structural elucidation. For example, we can do secondary and tertiary structure of a protein to determine denaturation. If the protein has gone through a thermal analysis, and then it will change its secondary structure, hydrogen bonding might be broken, you might break the alpha helixes and generate beta sheets. You can determine that by IR spectroscopy. What else? Yes, quality assurance of product. For the example I just gave you, did we achieve refinement? Is it 80% refined? Measure the ash content really quick and determine whether or not your mill is acting properly to refine your flour. What else? Lauren? Presence or absence of compounds, especially contaminants like the melamine in the infant formula. Okay, what else? Very important application for IR.
This is determining functional groups.
Look at the functional compounds to actually determine composition. So especially the major components of food, moisture, fat, protein, and lipid, as well as carbohydrates. What's the type of energy that is absorbed?
I just have another question. You keep bringing up melamine and infant formula. How prevalent, like how much of a problem is that?
Do I bring it up a lot? Yeah, I do. Okay, it's not prevalent now, but 2-3 years ago, maybe 4 years ago, there was an outbreak of melamine in infant formula in China. And at that time, everybody freaked out and they wanted methods to detect melamine in imported food. So that's why I've gotten those examples on melamine. But now I don't think it's a current major problem, but it is a contaminant that people watch out for due to the outbreak that happened a few years ago. Originally, it started with pet food, actually. So we had pet food contamination with melamine, and then infant formula as well. Okay. What type of energy is absorbed? Vibrational energy, very good. So IR is in the region that allows vibrational energy changes. Carries equivalent energy to allowable vibrational energy within molecules. Is mid-IR for milk composition determination a primary or secondary method? Again, what's the definition of a primary method versus secondary method? When we say primary method, what do we mean by that? Lauren? Official and validated method. So that's why it's called primary method. And why are secondary methods called secondary methods? Jill? They are calibrated by primary methods. So they are secondary methods because they need calibration, and we calibrate them using the official primary methods of analysis. So mid-IR requires calibration by primary methods of analysis. Mid-IR for milk and IR, near IR for any other compositional determination. Gone fast today. All right. Do you want to leave or should I start another lecture? Zach's going to ask a question.
What do you want us to do with our sheet from Friday?
Keep it. We'll continue with it when we start the protein lecture. There will be questions there. All right. Leave.